Good morning, Math 13. It's good to be back. I wish we were under better circumstances, but under the given conditions, this is the way we're going to have to do it. So I tried to just upload my lecture in PowerPoint directly to Canvas, and it just wasn't working out. There were some technical issues with the recording. So I'm going to be doing a combination of things. For this particular lecture, I've made a slideshow, PowerPoint, and I'll be talking over that. But I'm having to video it and then upload this to YouTube. It's the only way that you can hear my voice while I'm explaining the slides. For other types of problems, I'll just use the whiteboard here, and if necessary, I'll write on the whiteboard like I do in class. So hopefully we'll all get used to this new format. I know I've spent the last week getting my technology and purchasing all the various devices that are going to be needed for this lecture. So when we left off last time, we were talking about 4.2, Hamilton circuits and the traveling salesperson problem, also known as the TSP problem. So I'm kind of pick up where we left off. Last time we were together, I mentioned that we are interested in this traveling salesperson has to visit every city exactly once in the most efficient way. So that is the goal of this lecture. Before we jump right into the traveling salesperson problem, let's just talk a little bit about the terminology that we left with. Hamilton circuits, the main topic of this section. A Hamilton path must pass through each vertex exactly once, and that's all. A Hamilton circuit must pass through each vertex, but then return, beginning and ending with the same vertex. I like to think of it as the starting city. The traveling salesperson must end up back in the same city they started with. Remember, it is not necessary to travel along every edge. So as a warm-up example one, let's find any Hamilton path. Anywhere. Start at any vertex. So let's start at B. B to C, C to A to D. And that's it. B, C, A, D. We have hit every vertex exactly once. That is a Hamilton path. There are many correct answers. Okay. Well, ultimately, we want to make it back to the city that we started at. In this particular path, we started at B, and I would like to make it back there at some point. Let's take a different graph. Find a Hamilton circuit now. I have to hit every vertex exactly once and return to the vertex in which I started. So if I started at B and I went to D, then I go to C, and then I take this nice little highway over here to A, then ultimately I have to make it back to B. That is a Hamilton circuit. B, D, C, A, B. Again, there are many correct answers. Remember, to be a circuit, you have to begin and end with the same vertex to be a circuit. Next, we're going to play around with the graphs a little bit. I want to show you an interesting way to represent the graph. So suppose we have this graph. A graph can be thought of as a map. The A, B, C, Ds are like the cities, and the edges are like the roads or the highways or however you travel from in between different cities. But drawing this graph can be a little bit, I don't want to use the word annoying, but it can be annoying to draw these graphs. So we want to simplify this graph a little bit by taking this edge here and sort of tightening it up and bringing it inside of this triangle here. It's actually going to be a square, but let's just get to that in a second. So we can transform this graph into this graph. So we have the edges of a quadrilateral, A, B, C, D. I know originally it kind of looked like a triangle, but what we're going to do is kind of straighten this thing out a little bit, pull this out a little bit, make it look a little bit more square, and tighten up these lines a little bit. And we're going to get a much nicer representation. See how it's starting to look more and more square. And then finally, we'll just tighten up these edges a little bit. And our final graph is much easier to represent. So this is an equivalent graph as the original. And so if I wanted to do a problem involving a graph like this, it would be much easier to represent it like this in future problems. So that's exactly what we're going to do. Come on, there we go. So there's our nice graph, and we've added these red numbers here. The reason why I put them in red is so that they stand out. These are called weights. The values that are assigned to each edge are called weights. And this graph is now a weighted graph. As we go around the circuit, we're going to add up. We're going to sum all of the weights, and that is called the weight of the path. You can think of a weight as cost or distance or even time. Time is a form of weight. So when you think of a weight, I don't really think of it as an actual lead weight. You know, you're carrying around a 20-pound stone in your pocket. Well, I'm thinking more of how much does it cost me to go from A to D? Or how much does it cost me to go from A to B? And so each of these numbers gives you that cost. Or how far away is it? That's a different type of cost. Or how much time is it going to take me to get there? Those are the three most common types of weights that we see in our life. So find any Hamilton circuit and then add up all the weights. I like to start with A. Last time I was starting with B. You can actually start with any vertex that you like. So let's start with A. Let's go from A to D, D to C, C to B, and B back to A. So the weight is 5 plus 3 plus 9 plus 8. And so the weight of this path is 8 plus 9 is 17, plus 8 is 25. I don't know why my pen keeps making these things here. I'm not sure what's going on there. We'll figure that out as I get better at this. So again, if these were dollars, then that would be $25. If these were miles, that could be 25 miles. Or if these were hours, that could represent 25 hours. If it's not specified, the weight is just a value. So in this particular example, the value is simply 25. Complete graphs. A graph is called complete. My pen stopped working. There we go. A graph is called complete if every vertex has an edge connected to every other vertex. So this is what we call K3, a complete graph with 3 vertices. This one is called K4, a complete graph with 4 vertices. I know K is complete. I mentioned this in class. We use the letter C for something else. So we're going to be using the letter K for complete. This is the complete graph with 5 vertices. And finally, the complete graph with 6 vertices. They get pretty crazy as you go larger and larger and larger. For this particular presentation, I'm going to stop at K6. What we're interested in complete graphs is how many possible Hamilton circuits are there. If there are n vertices, there are n minus 1 factorial possible circuits. Let's see an example of that in just a minute. The traveling salesperson problem, we want to find the Hamilton circuit for this particular graph of the least possible or the smallest possible weight. There are 4 different methods that we're going to learn in this lecture: brute force, nearest neighbor, repeated nearest neighbor, and sorted edges algorithms. These are all various algorithms, step-by-step procedures in order to find the smallest possible weight. Let's handle them one at a time. Brute force. Brute force literally means what it sounds like. You're going to go through every possibility and pick the smallest one. So this is K4, complete graph, 4 vertices. So there are 4 minus 1 factorial possible Hamilton circuits. So over here, we've got 4 minus 1 is 3. 3 factorial is 3 times 2 times 1, which is equal to 6. So there are 6 possibilities to consider for this particular graph. 6 different possibilities for this graph. So we're going to list out all 6 of them. That's the brute force method. List them all out and analyze them all one at a time, and then pick the one that is the smallest, has the smallest weight. But again, I want to show you a cool way to represent this graph. This graph originally looks like a square, right, with A, B, C, D. But it sometimes can be confusing, the 27 and the 18, which one applies to which. In this particular graph, I mean for the 27 to be this entire edge, AC, and I mean for the 18 to be this entire edge, BD. All right, if that's clear, then that's great. But I also want to make it extra clear that this is not a vertex. If that was a vertex, then this graph would be K5 because it would have 5 vertices. That is an overpass. It means that these edges do not intersect each other, kind of like a freeway overpass. You have one going this way and you have one going underneath it, and they do not actually intersect with each other, kind of like a freeway overpass here. So you can imagine one going over the top and one kind of coming underneath like this, almost like a freeway, yeah, with a bridge going over it. So that's what's happening in this particular region here. So what we're going to do to avoid any kind of confusion or ambiguity is rearrange this graph again. And we do this by simply taking the D vertex and pushing it inside of the triangle formed by A, B, and C. When we do that, we can straighten out all the edges and sort of give it a new appearance of an equilateral triangle. A, B, C, D, A, B, C, with D being the center vertex. Now, I haven't changed any of the weights. So the weight AB is still AB, it's still 30. The weight BC is still 25, just like it was over here, it's still 25. So make sure that all the weights remain the same. AC was this inner diagonal here, that's now an outer diagonal here, it's an edge of the triangle, it's 27. And then you have your 3 inner bridges here, and now it's clear which one is which. 15 is AD, and if you come over here, look, AD was still 15, and so on and so forth. 18 is BD, BD right here was 18, and finally 13 was this lower side down here in the original diagram, DC. So this is the new way to represent K4. Complete graph with 4 vertices. So, the brute force method. We are going to list out all 6 Hamilton circuits. There are 6 possibilities. It doesn't matter what order you put them in. I started with A, B, C, D, A. It's basically alphabetical order. I'm going from A to B, B to C, C to D, and then D to A. We're going to add up all the weights, 30 plus 25 plus 13 plus 15, and the weight is 83. We're going to do this for all of the circuits. A, B, D, C, A, B, D, C, A. Well, we add up all the weights for that. We get 30 plus 18 plus 13 plus 27, so the weight is 88. Next, A, C, B, D, A. A, C, B, D, A. We add up all the weights of that path. 27 plus 25 plus 18 plus 15 gives us a total weight of 85. So far our winner is 83, but we have 3 more graphs to go. 3 more circuits to consider. The next one, ADCBA. You might notice something about it. ADCBA is just the same as ABCDA, but in reverse order. So of course it's going to have the same weight because you're simply doing the same circuit backwards. It would be like running the movie backwards. The salesman is running through each city backwards. So that's also going to be 83. You're going to find that the rest of the weights are simply the first 3 weights in reverse order. And so our smallest possible weight is 83. It turns out that in this particular graph, you have 2 choices. Both of them will give you the same weight of 83. So brute force works okay for a small number of vertices. It does work pretty well. You do have to analyze all of the possible circuits, but think about what could happen as the networks get larger and larger and larger. With 5 vertices, there are 4 factorial. Remember, it's always 1 less than the number of vertices. Factorial. 4 factorial is 4 times 3 times 2 times 1, which is 24 possible circuits. For 6 vertices, it comes out to 120 possible circuits. 7 vertices, 720 possible circuits. 8 vertices, 5,040 possible circuits. That would be a salesperson that only had to visit 8 different cities. There are 5,040 different ways to visit the 8 different cities. Imagine if there were 9 vertices, 9 cities, 40,000 different combinations in which a salesperson can visit 9 different cities. Well, let's skip ahead. A little fun fact here. You can impress all your friends and family. A graph with 14 vertices has 87,178,291 possibilities. Why don't we just call that a lot? 87 million Wait a minute. Correction. Billion. 87 billion. More than 87 billion possibilities. So even if we had a computer that could do 100 of these possibilities every second, it would still take us 28 years to go through all of the different possibilities. This is why the brute force method is not going to work very well unless there is a small number of vertices. So clearly we need another method to reduce the amount of time. I'm not going to spend 28 years on one math problem. Method number 2. Stay tuned. Next video, method 2.